So yeah, this is our third lecture. So as we had discussed I think I'll just review what we had discussed about surfaces because today we'll go further deep into surfaces. Yeah. So I was reading about manifolds. So actually, yes, sphere is a 3D manifold. Yeah, sphere is a 3D manifold, and curves are also, since they exist in 3D, right? So they are also 3D manifolds once they're uh, once they are in 3D. So it's as if manifolds is it's just that the curves happen to be uh, 1D space embedded in 3D, embedded in 3D, and surfaces are 2D space in terms of parameter, which is embedded in 3D. So both of them are eventually 3D manifolds. So, and we since we all the operations that we do are all are done in the three-dimensional from a three-dimensional perspective. And yeah, look, I mean, last time we had also talked about whether why not so surfaces, why do not we have this body mapping? The thing is, once we do not study the bulk of the body in differential geometry, we only look at a lower dimension space which is embedded in a higher dimension space. So that is the whole purpose of differential geometry. So we look from say Rm, which is some space Rm. Of course, we do not map the entire space. Some subset. Say we have some subset U, which is a subset of Rm space, and then we map it to another subspace, which is which lies in a higher dimension, such that m is less than n. So that's what we typically deal in differential geometry. If m were the same as n, then it's essentially we are just mapping in within the same space. So it's just like what we do in mechanics, where body is deforming, right? So even though the body lies in since the body lies in 3D, and after deformation, say we apply forces and loads, so it will deform because of that. So the body, even after deformation, still lies in 3D, right? So all that we are doing here is we are looking at the mapping of point to point in the in the same space. So in this case, R3. So that was just a brief clarification with respect to the last lecture. And today we plan to go quite a bit into surfaces, if possible, even do at least a major portion of it. So since we are left with 5 lectures, so what I plan is we'll have maybe 1 to 2 lectures, 1 to 1.5, I mean, at least 1.5 lectures on surfaces. And then we'll start discussing about a little bit on tensor calculus. And then we would directly jump into ruts and ribbons is what is the essentially the goal of this course. Okay, so in surfaces, what we are doing is we are mapping a 2D space or a subset belonging to 2D space to a 3D, embedding it into 3D space. So we are doing this by a map, which is sigma vector here, which maps from U to R3. Again, not the entire R3, I should call it V, which is a subset of R3. So it's like V3 is a subset of R3. So that's what we are going to do today. And the parametric space uh, is spanned by these two coordinates U and V. Generally speaking, that's what typically we use in the literature. Then we look at all the finer details of what we are trying to do. So we'll start with regular surfaces and also discuss what are called smooth. So essentially, all the surfaces that will be discussing in differential geometry, especially from an engineering perspective, is always needs to be smooth surfaces. There should not be any discontinuities. All the derivatives must be continuous. Then then we'll just look at a special type of surfaces called ruled surfaces. And I'm only looking at ruled surfaces, but I will provide also a few examples of other surfaces as well. Uh, just some sort of a, what do you call uh, just to give an idea. So essentially ribbons are modeled as ruled surfaces. Okay. And then we have this Gauss maps and Gauss-Wintergen map. Then we'll look at tangents and normals. Then we'll eventually jump into curvatures of surfaces, principal curvatures, and all other derived curvatures. So that's what we are going to look at. So formally, let's redefine. So we'll start our lecture with here. So it's lecture 3. So the way we define a surface is surface. It's of course an embedding of 2D uh, subset or a 2D set, or maybe fine, at best we can say 2D space to into 3D space. And then the parametrization of how do we define this parametrization of a surface? So since it's 2D space, then we can just parameterize it as a in terms of this some sort of a rectangular map, rectangular set, or rectangular region U and V. This forms some subset U, all these regions in this region, which is mapped to some general surface. So the way we do is, say at every U is equal to constant, we have these lines. So this is U is equal to constant line. U is equal to constant. Here also you have U is equal to constant along these lines. Right. So we'll have U1, U2, U3 till say UN. Just of course we'll be completely be covering this region if n tends to infinity. So these lines are will be mapped to some, say this line, this particular coordinate. These are known as coordinate lines. This will be mapped to this line here. I mean, of course, now it's a curve. So this curve here, and likewise, all these coordinate lines will be mapped to some coordinate, some curves on this surface here. So that is the whole point of mapping sigma, right? Now for the other part, you have V is equal to constant, and these are all constant lines, and they will all be mapped to, so say here. And in the limiting case, as n tends to infinity, you will this discrete set will become a continuous set, right? So these are called as coordinate lines. So these are coordinate lines. And this is typically a surface. Sometimes we prefer to call it a surface patch, but we'll not go into so much of technicalities. This is called a surface patch, and the collection of surface patch is what we call as a surface. But we'll not go into that in this class. Right. So ideally, essentially what it is sigma where is a map from U to V, right? This is some V set, and U belongs to R2 and V belongs to R3, or is a subset of R3. Okay, so far so good. Now we assume that sigma vector is a smooth map, which implies that all the derivatives of sigma are continuous. That is what we mean. So given that we have, so let's pick a point here. Let's call this point as u comma v, and it's mapping here. Say it's 1 2 say 1 2 3 4, right? Let's just call it again 1 2 3. So this point, right? So this is the point P where it's being mapped, right? So P vector is not, it's just equal to sigma vector u comma v, right? Now at any point P, at a point P, we define the tangent vectors as, so at any point we see that it's always formed by an intersection of two different coordinate lines. One is u is equal to constant coordinate lines, the other is v is equal to v is equal to constant coordinate lines. So in a sense that if we differentiate sigma by u, then we'll have a line which is perpendicular. So it's as if it's giving us the direction of the increase in u, right? So it gives us the local tangent. So it will be, let's take an enlarged picture here. So let me just take an enlarged picture, right? So let this be uv. I'll make it a proper curve. Right? So these are all we had used. This is u is equal to constant is black, right? So let's call this as black, and this as yes. Okay, so in a sense that these are u is equal to constant coordinate lines. This is u is equal to constant, and this is v is equal to constant lines. So in a sense that u is increasing in this fashion and v is increasing in this fashion. So we have this point P here and the local tangent. So this particular line seems to be a parameterization since u is a constant here. So you'll have sigma vector u naught comma v, because this along this line u is constant. Okay, and along this line here, along this line v is constant, right? So in a sense that this will be mapping some sigma u comma v naught. So this is constant and v naught is constant. So it's as if we have a curve. So it's as if we have this gamma vector v is equal to sigma vector u naught comma v, and then some say different, let's call it some, so we have gamma, let's call some delta vector u is equal to sigma vector u comma v naught. So these are like lines, these are curves, right? So and they happen to be a function of one parameter. And we know very well from the definition from the curve that the derivative of the mapping with respect to the parameter is what gives us the local tangent vector. So in this case, v is the vector. Sorry, v is the parameter and gamma vector is the mapping. So the tangent here will be, this tangent is, right, so this along this line v is varying. So this is given by sigma, partial sigma by partial v, right? And then we'll have another one more tangent vector which corresponds to, so this is our gamma v, this curve is our delta of u. So the other vector is partial sigma by partial u, which is this vector. So partial sigma by partial u. So
And yeah. And will
yeah,
there
yeah,
be any, yeah, will there be any relation direction wise in between del sigma del V and then del sigma del U?
yeah. So there is where this definition fall. I mean, comes right. So we have this two tangent vectors sigma. With this is tangent. Of course, there are infinity of tangent vectors, but we are particularly interested in these two. And the reason being is both are formed along coordinate lines. So both of them are along coordinate lines. Now what we see is that to define what we call as a regular curve. So regular curve is what we are interested in. Oh, sorry, regular surface is a surface for which partial sigma vector by partial u cross partial sigma by partial v is not equal to zero vector. So ideally, there is no such explicit relationship between them, but it just, I mean, this happens to be some sort of implicit relationship. Of course, it's vague, but still it says that these vectors must not be parallel. So I sometimes we use this abbreviation. I mean, we write in a short form notation. We call it sigma vector. U subscript means partial sigma partial u, and further sigma v. Right. So in a sense that this implies that sigma u cross sigma v is not equal to zero. So that is what we are in.
Yes, means they are not perpendicular and then they are along the U's and the V's. So,
Could
I
you
mean,
please repeat?
what would be the implication of having this value as zero?
Okay, so if it's zero, then what happens is uh, it's like it does not make sense. Like we cannot do many such operations here. So let's just see, right? So if they happen to be parallel, so it just becomes some degenerate, and it seems that this is not useful for us, these surfaces, because you cannot have physically you cannot have such surfaces. So you just take
Right.
a look. Just say that
Yes.
okay, these are just falling closely, right? So it's as if it's not even a surface anymore. It's some sort of a degenerate curve. So we have this
Yes.
surface like this, and all of a sudden this has become something like this. We just have a some sort of a some sort of a curve towards the end. Because in only in that case you can have both as parallel, right? Only in that case sigma vector can is parallel to sigma v. Only so that it only for a tangent you will have only for a curve you have unique tangent only for a curve, and since they are parallel, which means that it's pointing along the same direction, so to speak, then it's want some sort of it. Then this part cannot be considered as a surface. So overall, the mapping is not a surface because it leads us to local curve-like structures.
Yes.
That's just geometrically speaking. I need to further know read about this. Why is it the case? But geometrically speaking, at least we can see this with our own eyes here. That why is it so? So these surfaces are called regular surfaces, and we are interested only in regular surfaces. And I think geometrically speaking, we could figure out the reason why is it so. Right now, what we say is sigma v and sigma u. So you have these two tangent vectors. So these two tangent vectors, if they are linearly independent, so if sigma u and sigma v are linearly independent, which is of course because of their virtue of their cross product not being zero. So I should say since, because we have already determined that they are not they are linearly independent. So since sigma u and sigma v are linearly independent, we define something called as we def or we actually we have uh, uh, some sort of a say 2D subspace for which which is spanned by sigma u and sigma v. Now let's see why. So we have this u sigma u and sigma v, right? So what happens is if we choose any other curve, say any other curve for which sigma happens to a function of u comma v both, then their tangent will also lie in this plane. So these two linearly independent vectors, they define some sort of a plane. So some sort of a plane with origin at the point P vector itself. So this is sigma v and this is sigma u. And all the other points, I mean, they define something called as a tangent plane. And it's usually typically written as T. P means where it's centered and S means it's a tangent plane at point P of the surface S. So this surface is called usually denoted as S. So this surface is usually denoted as S. I'm using V just to denote the subset. Right? Now, so which means that TPS is a tangent plane, which is defined as the span of sigma u comma sigma v. And all other curves, whichever all the curves which are passing through P, its tangent, any curve which passing through P will have its tangent which lies in this tangent plane. Actually, we can prove that as well, but for the sake, I have proved it in the previous lecture notes. So for the sake, let's not go into proof today. We'll just take it for granted that we have any curve, the tangent will always be. So any curve gamma dot, right? The tangent will always lie in this plane. Right. So it's some sort of a 2D local subspace. Fine. Now, then using these ideas, now we can construct all that. So now we can construct. So since sigma u and sigma v are linearly dependent, we can define a normal to the plane. So any plane is always characterized by a normal to the plane TPS as n vector is equal to sigma u cross sigma v divided by the norm of the same thing. And this norm in Euclidean norm. So Euclidean norm, as we know that it's just something. So the Euclidean norm of any vector x is square root of x1 square plus x2 square till xn square. Right? So we are using the Euclidean norm, and this normal vector is always going to be unit normed by the very definition. It is unit normed. And by virtue of all the identities with regard to the vector product, you will have n vector dot sigma u is going to be 0 and n vector dot sigma v is equal to 0. These are just some trivial identities which follows from the vector calculus here. Right? So this is what is essentially we could define a surface. So we have a mapping. We could define uh, the basis of a tangent plane at any point P. And using that, we could construct a normal. So the surface normal will be something like this. It's always going to be normal at this point n vector. OK, so we were able to do this. Now let's go back to we were looking at some special surfaces we want to define, right? So special some sort of a surfaces. So one such surface which we are very interested in. Let's look at some common surfaces, some types of surface, some examples per se. Examples of surfaces. So say for example, you have this some say 3D. We can define something called as a paraboloid. Right? So here x sorry, x, y, and z. So the way we define this paraboloid is z is equal to x squared plus y squared. So this is one such example. This is also called as a simple paraboloid. Okay, from the very look, it seems that okay, it's just some Cartesian relationship, but how do we write it in a parametric form? So in parametric form, we'll write it as, we'll take u is equal to x, v is equal to y, right? And then using that, we can construct sigma vector takes u and v as input, and the output is the x coordinate of the mapping is x, is u, the y coordinate is v, and the z coordinate is u squared plus v squared. Right? So this is in parametric form. This is how we write. Right? So like this, we could parameterize, and of course, in one of the previous to this our class, we had also defined how do we parameterize a sphere and all. Right? So today we'll look at one special surface, which is called as a ruled surface. And we'll try to understand this what you call rule surfaces at length, since this is a very useful surface for our analysis. So how do we define a ruled surface? So that is the first thing. So a ruled surface is a surface that is a union of straight lines. And which are also called as the rulings, or sometimes the generators of the surface. Okay, so that is the definition. Now let's try to construct it, what it actually implies. So say it says that it's a surface that is a union of straight lines called the rulings of the surface. Right? So the way we would like to see it is, consider this some sort of a line, some sort of a curve, say gamma vector u. Then this surface is formed by a union of straight lines. So it's as if you have these straight lines. Just take a collection of these straight lines. And if we bring all these straight lines very close, then it will form some sort of a, this will eventually mimic some sort of a surface, right, with some curve passing through it, which is gamma of u vector. Right? It's provided we bring all these lines close and very close enough, right? So this is what we call as a ruled surface. So these are called as rulings. These are all rulings. These lines are rulings, or even generators. And this gamma vector is sometimes called as a directrix.
So, will there be any relation in between the angles of the lines and the curvature of the curve found? I mean, by taking the union of the lines.
Yeah, actually, the thing is, the angle itself will become a function of this parameter u. So this also the along this line u is also increasing along this particular curve, and this particular line, say we have this point as q vector. Let's say that this is q vector. So this q vector is the point Poisson vector of the point which is intersecting the curve with this particular ruling, the one we see it, right? So along this ruling, these rulings are characterized by some vector delta, which is also a function of u. So this is the, and this delta vector is of course it's a vector valued function, and it will vary from placed from along at every u, right? And any point on this ruling is what we had just some time back learned. This point P is analogous to the point P that we had here, this point P. So it's a point on the surface, right?
Yes.
Right. So we could make a connection between both these types of I mean, the general surface, and we are looking at specific surface which are called ruled surface. So which means that, and along this curve, along this particular ruling, and these are all straight lines, mind you, these are all straight lines. So there will be some parameter which is changing along those lines, and which always has a value of 0 at the on the directrix. So this v is always, v is a parameter along this, right? So which means that any point p vector, so it's like the p vector is given as uh, gamma vector u. So of course, still here it is gamma vector u. And then we use this vector addition rule. So this will be plus. So this is the point. Gamma vector u is the Poisson vector of q vector. So this is the q vector plus direction is given by delta vector u. And the how much length we are moving along this line, along this particular ruling, is given by the parameter v, right? And we could clearly see that sigma vector u comma v, we can now clearly see how it is, how it is a surface parameterization, right? It's gamma vector u plus v, and then v will vary from some uh, minus of some quantity minus v mean and greater than v. So I'll just call it minus on, so that it implies that all the quantities are positive in nature. So which means that v takes up, v is equal to 0 on the directrix. So this is what we call as a ruled surface. And now we can clearly see that this surface happens to be very familiar to us. Right? It's a very familiar surface. We see it every now and then. An example, one such example is, let's take a look at the glass tumbler and remove the base. Just remove the base. Just consider it's as if it's some hollow, right? And then we can clearly see that if we mark, say, let this be some sort of a curve which goes along both sides, right? So this we can call as the, let me use a different color. Let's let this be this. Let this be the directrix, and these red lines are the rulings. Right? We could easily formulate this also as a ruled surface. So even this, the surface of a glass tumbler is also a ruled surface. Let's take a look at the cylinder. Of course, it's very trivially a ruled surface. So we have this cylinder. These are all straight lines, right? These are all rulings. And this is the directrix. And we can mix, and just wonder, using this concept, we can make very, what do you call, interesting surfaces as well. Even some very different looking surfaces. Even these surfaces are also ruled surfaces. Right? So
So
these are all.
this idea of directrix is not that clear. I mean, especially when you wrote this, the interval for the possible values of v.
Okay, so V, the thing is V is always transverse to the directrix. So directrix is always a curve. So it's as if the backbone of any ruled surface is this curve. So this
Uh,
curve is directing, right? It's directing how the surface is.
so then there could be many directrix. Like say, I can start from the extreme right of the
Exactly,
first line
exactly.
and
So it's not unique. Directrix is not unique. Right. In this case, you can start anywhere. This can also be directory. You can have infinity of directories, but we chose one particular and then define the end limits for V so that uh, it becomes things are a bit simpler, right? So we chose one particular V, one particular sigma or gamma vector, and then we defined the upper and lower limits for V, and then we had some parameterization.
okay,
It's
yes.
not unique, yeah. It's just how we choose a directrix and then define a surface based on that. So in this case also we have, so likewise here also we have, I'll just remove all these black lines so not to confuse. So we have chosen some directrix and then built a surface around that. So these are all rulings. Yeah, these are all rulings and they can be in 3D. This is some sort of a, it should mimic a 3D, but yeah, I am not a very good artist, but this is some say twist, some very not regularly deformed configuration of some strip. So ideally we had this some sort of a strip like this with rulings like that and some rectangular strip with this as the directrix. And this was mapped like this by applying forces and moments to get this deformation. Right. So we can now understand how general these rulings, how we can have so many different types of surfaces, which we can idealize it as a ruled surface. And ruled surfaces are very interesting. It has some very good properties, and we'll come to know gradually as we discuss further on this. Now, since we have many such ingredients in our hands, let's look at some of the conditions for a ruled surface to be regular.
So can
So
you give an example of a surface and
yeah,
which is not the ruled one?
okay. I mean, the thing is, say for example, sphere. Sphere is not a ruled surface,
Yes. Yes.
right? An
Right.
example of sphere was a ruled surface. Ruled surface are just, of course, let me just put it here. Ruled surface are a subset of surfaces, just a proper subset of the general class of surfaces or even smooth surfaces. And many a time, some surfaces would not look like ruled, but they happen to be they happen to be ruled. So it's something strange. Things like a hyper paraboloid is a ruled surface, but it doesn't seem so very intuitively. So this surface, right? This is a ruled surface when you have an hyperboloid surfaces. And the way I don't know, it's like I don't know how to construct it, but it's always made by construction of these straight lines, which are just rolled, what you call rotated, and then you can construct this particular hyperboloid. So some surfaces are very strangely, but they are ruled. They can be posed as a ruled surface in a very strange sense, but they are also ruled surface, right? But we are not looking into hyperboloids here. Okay, now let's once we have the parameterization was sigma vector u comma v is equal to delta vector u, and we had delta vector, sorry, not delta, it was gamma vector u plus v
V delta V delta.
delta I. Right? So this was our ruling. This was the ruling, and v is just the parameter which is transverse to the directrix. Now let's take a look at the tangent vectors. So the tangent vectors, or rather, since there are infinite of tangent vectors, we'll call it as the, let's call as the basis of tangent vector. Of course, they are also infinite, but the basis which is easily constructible basis of the tangent space TPS, right? So, of course, in our scenario, it is going to be okay, TPS, yeah, TPS, fine. So sigma vector U is equal to gamma vector. So we recall that we could use dot to imply a derivative with respect to U, since it's a OD, since it's an ODE, plus, and V is not a function of U. So U and V are parameters or independent variables. So V into del dot U, right? Likewise, sigma V is, so of course, partial gamma vector by partial V is 0. So we'll, all that we have is del vector U. So let's write something called as condition for regularity. So all that we know is that gamma vector, sigma vector U cross sigma vector V must not be equal to 0 vector. So that is the condition for regularity. Let's just take a look here. So gamma vector U plus V del vector U cross del vector U is equal to gamma vector U cross del vector U plus V del vector U cross del vector. So this is one such scenario. Now, based on this, we'll try to construct. So either this should be not 0, at least in the sense of at least, either this should not be equal to 0, or this should not be at the very least. Right? So what we can say is that if gamma vector, say, happens to be, uh, so it's like, so these are the conditions. So of course, they will not be exactly equal to this, equal to the same, but so these are the, at least, I mean, these are the conditions for it not to be regular, and we'll deconstruct it later, what all possible, because once we study curvatures and all, then we can go further deep into what we are trying to discuss here. Right? At best, we can say that gamma vector is going to be locally tangent. So we have some, let's say, this as the directrix. So this is the gamma vector U, gamma vector, and then this will be our del vector, right? Del dot vector. It's also going to be, uh, uh, yeah, wait. But the thing is, del vector is always going to be, uh, let's take a look at the figure here. So del vector is, these are all straight lines, right? These are all straight lines. So which means that gamma vector, del vector, the tangent along del vector is this nothing but del vector itself a tangent, right? I mean, if you go by that, it's some sort of a, it's some sort of a pointing vector. It does not say much about, these are all straight lines. So this is del vector. I think there was something which we could deduce from these conditions, that something should not be parallel. Uh, so del vector dot U, del vector dot U may or may not be, del vector dot U may or may not be perpendicular to. I see, I see. There was something here. No, okay. The thing is del dot U. should not be the same as del u. That was one such condition I had read in some book. This should not be there. How can we visualize it? Del dot u requires information of the local of the adjacent. Rollings. Okay, we'll get to know this. This I had read in some book, so I did not try to understand at that time, but this was one such requirement that you should not have del dot u as parallel as del dot u as del u. So we'll go get into that. I'll just mark it for review. And so this was one such surface, which is ruled surface. And then we'll take a look at one more interesting types of surface, which are called as the surface of revolution. So any surface which is axis symmetric in nature can always be posed as a surface of revolution. And all these surface of revolution have something called as a they are defined by something called as a profile curve. Now let's take a look at some example. Say you have a vase, right? A flower vase. So with its axis of symmetry like this is the axis of rotational symmetry. And if we place it in XY coordinate frame, then we can have something called as a X. This is Y. This is Z axis, right? This is the origin. Now let's take a look at the thing that lies just on the say XZ plane. So ideally we would have this as the XZ plane. So in XZ plane, you can have this as the profile curve. Right, so this is in the XZ plane. These are XZ plane. So on this is our XZ plane. So on the exact plane, it would just look like something like this. This is Z, this is X. So on the exact plane, it would look like right. So this would be our profile curve. Let's call it red. And once we rotate it about Z axis, then it will form that particular the surface of a vase, right? Once we rotate it, then trace out all that surface of a. So this profile, if we look at, so this profile seems to be some sort of course, it's a 3D curve, but lying in XZ plane. So let's call it as gamma vector U. So these are profile curve. Gamma vector U is equal to f of u, since it's f of u implies the function behavior of this curve and its component in along x-axis, f of u, and the profile curve has no component in y direction, so 0, and this has g of u, and u starts from here and goes to the top, right? Once you rotate this profile curve, then you can define a surface, right? So rotate gamma vector u about z axis. Then we trace out the surface, which is sigma vector u comma v. This is equal to f of u, right? F of u. And then it will have traverse some angle. So this v is the angle, right? F of u cosine v f of u sine v, comma, g of u. Now see, we could easily trace out a curve. So what we have is, let's write it clearly here. So sigma u comma v is equal to f of u cosine of v, f of u sine of v, g comma u, right? And u is the parameter for uh, profile curve, and v is the measure of rotation.
So why did we keep 2f common and the other one is different? So we could have kept all f's or
Okay, the thing is, yeah, could you please repeat? Yeah.
so we could have made we could have made this all different, like say f1u, f2u, and then f3u. I mean all different, all three different.
Okay, the thing is, now let's take a look here. Put v is equal to 0, which means no rotation about z-axis. Then it gives us
Yes.
sigma u comma 0 is equal to cos of v is 0, 1, right? And sine
Yes.
of v is 0, and you have g of u, right? We got back our profile curve. That's what we wanted.
Yes. Yes.
So that is the reason that f of u are just some functions. So in this case, surface or evolution, we only need to define one profile curve. Once we have the profile curve, then we can create the whole. And I believe this is how even I mean all those in manufacturing, all that any surface of revolution, if you want to create, then we just have to prescribe this profile curve, and it will just generate based on that.
Yes.
And this is also used in CAD and all the parametric modeling in CAD, that you have to give profile surface, and then we can generate the entire the surface or evolution based on that,
Yes.
right? So that's the reason. But now you'll ask, okay, things are fine, but the question is, do we have constraints on f of u and g of u? These are some general functions of u. So are there any constraints on g and f of u and g of u? So these are some just questions which come to our mind because we have chosen arbitrary functions, but they cannot truly be arbitrary. There has to be some restrictions, right? So geometrically speaking, let's take a look at f of u and g of u. So f of u was supposed to give us the distance um, of the profile curve along x direction from this axis of rotation y. So this is f of u. Right? So this just gives us the distance from that. So what you can see that from the very what do you call, from the very geometric representation is that f of u must be greater than 0. That is definitely the case. Right? Otherwise, we cannot generate a surface or revolution if f of u is less than 0. Then because then you will be trying to will be trying to penetrate into the surface itself while we are generating, which is not possible. Right? So suppose this curve was something like this, and then we were trying to generate. It's not possible, right? It's not. We cannot even imagine any such surface being created. So say if this was the surface curve, I mean the profile curve, then we could not have, so this part only would form, but this part we cannot we cannot be able to form a surface from because of this part. And in this part f of u is less than 0, right, since it is along the negative x-axis in the exact plane. So that is the
Yes.
reason we have always this constraint, f of u must be greater than 0. Now let's look at other things that we always want to check about the regularity. So say sigma u. And there are no constraints on g of u because g of u can be negative, positive, doesn't matter. It's just along the z-axis. Of course, even in this case, g of u is negative from the portion of the curve below x-axis, while that above x-axis is positive. So there are no constraints of G on G of U, except that G of U should be continuous, at least, right? So at least this should be continuous. From a manufacturing point, I'm not asking it to be smooth. The reason because if you want a sharp turn on our surface of revolution, say for example, this sharp turn, right? So in this case, we can clearly see that G of U is not differentiable at this point. So we would only want G of U to be continuous. That's it. Differentiate it because then we would not be able to produce surfaces with these sharp edges.
Yes, yes.
But yeah, but since we are dealing with smooth surfaces, then we want even G of U to be smooth. Right? So going back, you have sigma of U is equal to, let's denote any derivative with respect to U as just dot. So F dot U cosine V, F dot U sine V, comma, G dot U, right? And likewise, sigma V is equal to, so you have F of U, then derivative of cosine V is minus sine V, so minus sine V. Likewise, F of U, derivative of sine V is cosine V, comma, and G does not depend on V, so it should be 0. Right? And since in this case, we even have the representation in the components, the representation of the vector in component form. So we can even do our the cross product, right? In component form. So sigma U cross sigma V is, let's just call it as E1 axis, E2, and E3 basis vectors. And this is F dot, and I'll not take the arguments for simplicity. F dot sine V, G dot, and here minus F dot sine V, F dot, sorry, it's not F dot, it's just F minus F sine V, F cosine V, and 0. So this gives us that for E1 component, we have F dot sine into 0 is 0. So we have minus F G dot cosine V E1. Likewise, for E2, we have minus F dot FG dot minus FG dot sine V, okay? And again minus 0. So all that we have is minus FG dot E2 plus for E3 we have F dot cosine square V plus, and then we have minus into minus of plus. It should be F dot, sorry, plus F dot sine square V, and then E3. So let's take a look now. So we'll have, if we simplify it, F G dot cosine V E1 minus F G dot sine V E2, and for this part we have F into F dot E3. Right? Now let's take a look at the norm of sigma U cross V, since there is where we can get some idea about what can be the regularity condition. So square root is F square G dot square. So this is, right? Cosine square V. Let's make some space. Plus F dot square G dot square sine square V plus F squared F dot square. Right. Again, we see some cosine square, sine square come into the picture. So we'll just take a simplify that as well. So F square g dot squared sine square is 1, so plus f square f dot squared and is equal to, and in both the terms we see that f square is common, so why not take f outside, and we'll have g dot squared plus uh, f dot squared. Now let's try to gain some idea from here. We'll use both the properties. One property is very fundamental property, what we call as say uh, due to norm. So due to norm, what we know that norm is always greater or at least equal to 0, right? So what we see is that this term is of course positive because it's the square root of root g dot square plus f dot square. So we need to worry more about f, right? So which means that due to norm, it says that f must be non-negative number, which is that f should be greater or equal to 0. So that we could know, that we have figured out.
But then
Just
this was
from no,
already a, yeah. But then this was already a condition that f is positive, f
no,
is greater than zero.
no. The thing is, this we wanted to this we what you call arrived at from a geometric point of view.
Right, right, right.
So this was just a guess of ours. We just guessed it. We were just guessing. Can this, because it seems very obvious from the way we define profile curve and the root. So we were just guessing it, and we could see that we could prove it mathematically as well, that it's true. But what we have not yet, we have established that it should be non-negative, but we need to establish, we have one another property set to satisfy. So it was just from norm we could get to know that f should be greater or equal to 0. However, we also have something called as a regularity condition. So from regularity condition, we have an additional requirement that sigma of u cross the norm must be greater than 0. Because of course, since we are not allowed to have the cross product to be a 0 vector, and since the norm is always going to be greater than 0, which means that this will always be greater than 0, right? Because of which this implies that first of all, either f of f has to be greater than 0, and even the square root part g dot squared plus f dot squared also has to be greater than 0. So this is our most the regularity condition enforces a strict requirement that f has to be 0, has to be greater than 0, and also that root of f dot square plus g dot square has to be greater than 0. This is of course well known, it's very true, but in a sense that this must not be equal to 0.
Yes.
Right? So these are the conditions for our when we define a surface of revolution, then the profile curve must satisfy these requirements. F of greater than 0 is of course we could even see it from the way we have from geometric point of view, but the second requirement f dot square plus z dot square is greater than 0 is this is the requirement on that as well. Yeah, so this was what we wanted to discuss in just the examples part. Now we'll jump to understanding some of the measures on surfaces. So we wanted to talk about tangents, derivatives, and all. What all we had in plan is okay. So now we'll take a look into, before we even go into the Gaussian maps and all, and tangents and normals. Of course, we introduced the concept of normals, and tangents also we have already introduced. So before that, let's go into something more fundamental for a curve, for a surface. One of which is, of course we know what a surface is. Right? We know on us, we know how we know about the surface and all. But we would like to take a closer look at how do we define lengths? How do we measure? Because for engineers, we always we want something to measure. It has we must have we would always want to have some quantitative idea about the system that we are dealing with. So the question arises, how do we measure, say, entities on a surface? So entities can be of, at best on surface, you can have curves and at the max area or a portion of the surface. And once you have portion of the surface, this implies that we want some area, some measure called area. So for curves, we want length, and for portion, we want the area. Right? These are the entities that typically can exist on a surface. So let's say we have a surface, right? And we want to measure the curve from A to B. Any such curve, say like that, which lie entirely, this lies entirely in S, and S is our surface. So this curve lies entirely, and we want to know what is the length of the curve. What is the length of the curve AB? So of course, since we are dealing with the lengths of the curve, then of course first of all we must define that curve. What is that curve? Right? We have to parameterize it first. Parameterize this curve first. And recall we had defined the length of a curve in our first lecture. So given a curve, let me just reproduce it. Given a curve gamma vector S, right? Then the distance or length of a portion of a curve was, in this case, it was just S, right? Because S is all arc length coordinate now. It's already arc length parameterized. So we must mention it given a unit speed curve. So we want to know for a general curve. So given a general curve, not any specifically designed, specifically parameterized. So given a general curve, and we call it gamma vector as a function of t. So in that case, the length of the portion of the curve of portion, which means that t is an element of t0 to t1, right? Just we want to know just this portion of the in the parametric space. Then we saw that we have to define it. First of all, need to find the tangent vector, take its norm, multiplied with the small increment dt, integrate it from t0 to t1. And this gives us the length of the portion of the curve, right? This we recall very well. Now, for a surface, what happens? A surface is parameterized in terms of u and v, and the mapping is given by sigma vector. So any point here, say this point, let's call it u comma v. Then we want to and we know very well that it's not easy. So since every point along the curve will lie on different coordinate lines. So this is one such, these are the coordinate lines. This will be different coordinate lines. So let me use a different color here. Right? So you see that it's not very straightforward to parameterize in terms of u and v, because even at every point you have a different combination of u comma v. So and all points on the curve lie on different coordinate lines. So which means that we cannot use this particular route. that just we cannot easily define. So what we do is we even allow that let u and v also vary. So in the parametric space, right? In the parametric space u comma v, we want to this particular curve will look something like this. So we want so it seems some sort of a curve, right? It seems some sort of a curve even in parametric space. And because it's a curve in parametric space, we'll define some parameter t u which is the independent variable, and the parameters of the surface are themselves a function of t. So it's as if we are defining t from here and then moving along the curve here. So which means that every point in this case, it will be u comma t comma v comma t. So it's as if our parameterization is sigma u comma t v comma t. So this is now a curve which we can call it gamma of t, right? Because now we can clearly see that the entire surface, the curve lying in the surface is a function of a deeper parameter. If you go by that, ultimately here t is the only parameter, right? So here t is the only parameter. So ideally, mathematically speaking, we are doing something called as a composition of maps, right? We have one map which takes us from t frame or the t space from 0 to some number, and then we map it to a curve in the UV plane, then use another mapping to take us to the surface, which is this. This is mapping is sigma, and this mapping is some say phi. So strictly speaking, this is a sigma o phi of t. But we'll not go into all this composition of maps and all. Let's not go into that unnecessary complications. We'll just stick to what we are doing. So once we have a curve, then we know what to do. First, determine its tangent vector. Determine gamma dot. Now, so gamma dot we have to determine. So then we have to use this chain rule, as we would like to call it. So we'll have gamma sigma by u dot du by dt plus gamma sigma vector by v dot dv by dt. Right? We could now see, and let's make it slightly more compact, is call it gamma u, sorry, sigma u, u dot plus sigma v, v dot. Right? In a very nice notation, all of which are function of t. This is a function of t. This is also function of t. Now what we need to do is need to determine the norm. So gamma dot, the norm of this is going to be square root of, first of all, this has to be equal to the square root of gamma dot t dot gamma dot of t. So which means the square root of the inner product. So why not? Let's try to determine the inner product. And I'll skip this t for now. Omit this for now. Then you have sigma u, u dot plus sigma v, v dot. Take dot product with itself. So we have sigma v, v dot, right? Now let's go. Let's do all that expansion. So you have sigma vector, sigma u and sigma u. They are vectors. So sigma u dot sigma u, and then u dot squared plus we have sigma v. Let's go in this fashion. So sigma u dot sigma v, u dot v dot plus sigma v dot sigma u, u dot v dot plus sigma v dot sigma v, v dot squared. And you know that the inner product, they're commutative in nature. So this eventually becomes is the same as twice of this. Remove this, we'll have this, right? And all that we have to do is, these are all scalars now. These are scalars. These are all, they have all become scalars. Now we can do all that. Take the norm of this. The norm will be just square root of this, right? So this will be equal to square root of this quantities. Now let's just, for the simplicity, let's rename these quantities. Let's call it sigma u dot sigma u as E, sigma u dot sigma v as F, and sigma v dot sigma v as G, right? So we could simplify, we have to just simplifying it. So you have u dot square plus 2f u dot v dot plus G v dot squared, right? And then multiply both sides by dt. So dt, right? And then integrate it over the t naught to t1. And this gives us uh, the length of the curve which is lying in the surface. Now let's come to something which is really interesting here. When you, let me again bring this, copy this into this new page. Remove this integral part, but let it still be multiplied with dt. And we know very well that gamma dot, the norm of this dt, is nothing but it was just d gamma by dt into dt, right? So, and then dt is always positive in nature. So which means that we can bring dt out. It will be, so this means it's an infinitesimal length along the curve. Infinitesimal length along the curve. Likewise, if we repeat the same for this quantity, then what we have is this quantity is as it is. And you recall that even u dot is nothing but du by dt. And then bring all the dt squared outside the square root, just dt, and it's in the denominator. So this dt cancels out. So you have square root of e du squared plus 2f du dv plus g dv squared. So far, so good. Take the argument of the square root outside and just put it here. You know that everything we could do, this calculation of distances, was solely because of this. And I'm telling this because this is what we call as the first fundamental form of surfaces. And this is the first fundamental form, also denoted as I, the one in Roman script. So I'll just highlight it. So first fundamental form, what it does is it gives us an idea of, or it doesn't give us it gives us the length, or gives us the notion of lengths on for a curve, lengths of a curve, of curves lying on a surface. Right? So far, so good. It gives us the lengths of the curves lying in the surface, and the coefficients E, F, and G are the coefficients of the first fundamental form. First fundamental form. So we get an idea about the distances and all. So E, F, and G are what is very relevant here. And they also, the first fundamental form also helps us in getting the angles between two curves when you, I mean the angle of intersection of two curves on a surface. So we have this surface here. Right, so we have this surface here. Right, and then any two curves, this curve and this curve. So what is the angle at which they are intersecting? So this is a gamma vector, and this say we say some phi vector. That these be two different curves. So what is the angle of intersection here? So provided that the parameter of gamma is some t, and this is some say s, right? So this is some say t, and let's not use s because s typically don't denotes outline parameterization. We'll call it some say r, right? So what they will help us is in cos theta is nothing but, and you know that at any point p vector e and f are unique at any point, no matter which what curve is passing through it. So e, f, and z are unique at any point. Unique at for every point. Sorry, it's for every point p on a surface. No matter what curve is passing through that point, doesn't matter, right? Now cos theta is given as e u dot u tilde dot, and so I'm using u dot to imply coordinates along u comma v along this gamma curve, and u tilde comma v tilde as the parametrics, the variation of parametric space in along the curve phi vector here. So this f u dot v dot tilde plus u tilde dot v dot plus g v dot v tilde dot divided by e u dot squared plus 2f u dot v dot plus g v dot square root, and then you have e u tilde dot squared plus 2f u tilde dot v tilde dot plus g v tilde dot squared. So this gives us an angle, and you can clearly see that E, F, and G is which occurs everywhere. I mean, in the numerator as well as denominator. So they are that fundamental. So, okay, we could find the lengths of the curves, but it so happens that even if the curve, say, even if the surface is deformed or say, of course, deformed. So say this surface, let's again draw a different surface here. So this surface, we had point to point here, the distance some AB. If it's say deformed to form another surface, something like this, right? So we had A become here B, A prime, and this is B prime. Even this curve will deform like that. So what happens is it if the surface is deformed without stretching it, just 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 what you call just bending it, then what happens, the distance between the curve A and B will remain preserved, right? So if the surface S is deformed without stretching without stretching then the distance or the length of the curve joining A and B and length and that of curve or that of deformed curve joining A prime and B prime are the same.
So, I mean, as per the common sense, it makes sense that the length would be same, but do we have some mathematical, formulation of this, that if it is not being stressed, then the length of AB and
Yeah,
A prime will
we can do that. Yeah, we can do that. So
okay.
what happens is in that case, the thing is again, I'm not discussing about this in this course is because although you will find it in the previous notes that I have shared with you in that
Okay.
folder. The thing is, I just want to keep the topic simple so that it's easy to pick up when we are dealing with mechanics. Because in mechanics and all, we won't be dealing with scenarios such as reparameterizer and all. That is the reason, because then what happens is it's as if we are deforming it. We are only deforming it. And what though that deforming is known as what I just forgot its name. It's sometimes called as isometry preserving deformations. Preserving deformation. And you know what the meaning of implies, right? Isometry is deformation in which lengths are preserved. So the mathematical requirement is that for an isometric deformation is I'll just let you know right away. Of course, I did not want to touch the topic because it's just it's not very relevant to us right now, but just for the sake, uh, let me just pull it up. So the requirement is that for iso deformation, for isometric deformation, the requirement is that the coefficients of first fundamental form. Sometimes the coefficients of the first fundamental form are called first fundamental form itself because the first fundamental form ultimately involves coefficients, right? So it's equivalent to saying the first fundamental form. It so happens that this expression is called as first fundamental form, and E, F, and G are coefficients of the first fundamental form, right? So either we can say that the coefficient of the first fundamental form of the reference and deformed states or the deformed surfaces, reference, or I'll just call it original, are the same. So which means that, so if this is S tilde and this was our surface S, of course it's surface S already, then the requirement is that E must be equal to E tilde, F is equal to F. I don't know if this really holds. Typically what happens is, okay, it should hold actually. And then F and then G is equal to G tilde. So then it means that you have the distances or the lengths between any two, the curves joining any 2 points are always preserved. So this is the requirement for isometric deformation, and we can prove it. It's just that it will involve a lot of parametrization, reparametrization, something called as diffeomorphism, which is they are like fancy sounding words, but fundamentally they are very simple compositions of maps. So one composition just some time back we learned about sigma O phi. That was one very simple composition of two functions. it will just involve all those compositions and a bit of algebra just to manipulation. So we can show this particular thing that holds true. So that was the whole uh, goal. But let's just give take some examples so that it becomes things become slightly clearer. These ideas. So what we'll do is I'll just pick up some example. Let me find some example. Uh, okay, let's look at surface, a plane surface, and then try to form a cylinder out of it. And we know that we are just rolling it about this particular axis, right? This axis, we are just rolling it up along about this direction, and then we get a surface. So let's look at the deformation, so to speak. So here, let our parameterization be like this is u and this is v, and in the circular case as well, to be consistent. To be consistent, what we should do is let's take as v, this as u. So likewise, this is u, v, right? Now, what we do is for a surface, the parameterization is given as any point in this p vector, right? So this I just want to refer uh, to the parametric space, not in the direction of variant. Okay, let it be here. This is just how the parameters would vary on the surface. That's what I mean here. So what we do is any point p vector on a surface will be represented as, for any point, yeah, let's call it p vector itself. So sigma of u comma v is equal to a vector, which means that some say this particular thing is, let this be the, or let this be the a vector, the Poisson vector of this end, this corner with respect to xyz frame, with the origin of xyz frame. So this is the a vector, and then we can traverse all the way here. Let me center this here, and here, or this also somewhere here, right? And then this particular point is nothing but a, and also be two. Let's take two vectors, r vector and s vector. So by vector addition, this point has a Poisson vector a vector plus something called u r vector plus v s vector. And you know that u and v are just the coordinates which will vary over the entire region, and then we can cover the entire surface. For the cylinder, we know very well it's essentially a surface of revolution. And again, we had also learned that it's also a what do we call a ruled surface, right? So what we do is, why not consider it to be a ruled surface, and we'll make some changes here. Or maybe I don't know what it would be easier. Um, let's consider it a surface of revolution. So it will be some straight line, right? This is some straight line, right? So the profile, which is in x and z frame. So the profile axis is going to be sigma of u, say v comma 0, v is equal to 0 is going to be just, it has only x component has some value. Let's call it some, say maybe some distance from here to here, some a, or maybe some constant. Let's call it say n, right? So n, so the coordinate is always n and then 0 comma u, right? Because the distance uh, it all, I mean the distance along this is the u direction, Now along which u varies, this n 0 comma u. So this is constant. So the profile curve would be given by 0 comma u comma v is equal to n cosine v n sine v comma and then u, right? Fine. So we have parameterized both of them. Now let's look at sigma u is equal to just r vector, and r and s are constants, are constant vectors, constant vectors, because they are, of course, they belong to a plane, and in plane you can have a fixed basis vectors, right? Are constant vectors. So sigma u is equal to r, and sigma v is equal to s, and let both of them be unit normed. Let r vector norm of this is equal to s vector be unit normed. This will simplify our things later. Now let's take a look at E, the first fundamental form. So E is equal to sigma u dot sigma u, and r dot r is 1. F is equal to sigma u dot sigma v, and we also recall that we are looking at the corners of this rectangular. This r and s are unit vectors along along the edges of this rectangle, and you know that edges are always perpendicular, because of which r dot s vector is going to be 0. And the same thing will apply here. R dot s is 0, so sigma this is 0. So g is equal to sigma v dot sigma v, and its s dot s is 1. Fine. So our first fundamental form is E du squared plus 2f du dv plus g dv squared, and using the values E is equal to 1, so you have u squared, f is 0, so no term from, no contribution from f, and then dv squared. Fine. Now let's look at this, our the cylinder case. So sigma u is given by 0, because n is not dependent on u, and cosine v is also not dependent on u. So sigma 0, 0, just this part 1. Fine. And then sigma v is equal to minus n cosine minus n sine v, and then n cosine v, and you have 0 here, which is expected, right? Now let's take a look at the coefficients. So E is equal to, now let's call it E tilde. So I should have called tilde everywhere. Okay. E tilde is equal to sigma U tilde dot sigma U tilde. And there is nothing but why is it 0 everywhere? Okay. Sine V, sine V. Yeah, I think we have parameterized in a wrong manner. I hope things are well here. So n dot n sigma u is 0, 0 v. Fine. U is minus n. Okay, sorry, it's fine. I don't know. It's fine. It's actually sigma u dot sigma u, right? Yeah. So it's 1. Then f tilde is equal to sigma u tilde dot sigma v tilde. And then this sigma u is perpendicular to sigma v. So this is actually 0. And g tilde is sigma v dot sigma v. And this again is n squared sine squared v plus n squared cosine squared v. And now I will just retrace things back, right? So this is equal to n squared sine squared plus cosine squared is n squared. So what I will do this as an afterthought, take n is equal to 1. So this becomes n squared is equal to 1. This is just an afterthought. Yeah, it's after we have backtracking everything. So what we have is the second fundamental, this fundamental form is E tilde The first fundamental form, this is the form one, is 2f tilde dv squared plus g tilde du dx will be du dv squared, right? So this will be equal to uh, du squared plus uh, just dv squared. And we see that they are identically same. Well, the thing is, I made one manipulation here that took n is equal to 1. And I believe it. I was trying this for the first time using a ruled surface, using this surface revolution. Can we not do it in terms of ruled surface? So let's take a look. Let's do it in terms of ruled surface. So we have this gamma vector, which is the directrix. So this is the gamma vector u, and the transverse will be some a vector, and the parameter will be v, which has a value of 0 at the point of intersection. So this will be sigma vector u comma v, and a vector it's purposely taken to be one unit. It's a unit vector norm, and in a cylinder that the tangent vector will be perpendicular to the rulings here. So which means that gamma dot a vector is going to be 0 by construction. It's by construction. So the parametrization here is gamma vector u plus v a vector, and a vector is always constant. A vector is constant because, of course, all the vectors, all the rulings will have the same direction. Right. Now let's take a look at sigma u is nothing but gamma dot, and this gamma also always chosen to be unit speed curve, as we recall long back that we'll always be dealing with unit speed curve. So gamma dot, and then there is no u come anywhere else. So sigma v is equal to just a vector. Now let's do sigma dot e is equal to e tilde is equal to sigma u dot sigma u. This comes out to be gamma dot, which is 1 because gamma is a unit speed curve. And then f tilde is equal to sigma u dot sigma v, and this comes out to be gamma dot a vector, and by construction it is 0. And g tilde is sigma v dot sigma v. This is also a dot a, which by construction is 1, right? And so our fundamental form is d u squared plus dv squared, and you know that they match. It matches with this, right? And you know very well that when we move from a rectangular platform and roll it into a cylinder, we are only deforming it. We are not stretching it. So it's a pure. It's this transformation is called as these are just isometric preserving deformation, because we did not stretch it. Only if we stretch the surface, we change the first fundamental form. If we are not stretching it, we are just deforming it, then we are always preserving the first fundamental form. So this was what we had to deal with such second fundamental form. Now you'll ask, okay, but fine, what all do we also need other fundamental forms? The thing is, through first fundamental form, we got an idea of distances. We got an idea of distances, lengths or distances, right? However, nowhere we realize that even when we are, say, rolling this cylinder into this rectangular sheet of paper into a cylinder, although we are not changing the lengths, but we are changing something else. We introduce some sort of a curvature, right? We introduce curvature into this surface. However, that is never captured in first fundamental form, right? So it's like curvature is not captured using first fundamental. So that's the reason uh, we had there was the need to introduce another fundamental form which would talk about curvatures, which would measure curvatures on surfaces, and there is where we come with the second fundamental form. So here is where we come need for second fundamental form. Of course, we would not go very much today. I think we had covered a lot of things today, but let's just set the stage for next session. So ideally, what we mean by curvature, right? In the context of curves, we could see that curvature gives us an idea of how the tangent vector is rotating, right? So curvature, it was the rotating of tangent vectors. How does the tangent vector rotate as we move along the curve? In surface, it becomes slightly more complex in the sense that now we have to imagine what curvature implies in terms of in the context of surfaces, right? So we have some sort of a surface like this, right? Some sort of surface like this. Maybe as it involves some 3D. Okay, it's not. Okay, let's have this some sort of a surface. Of course, I'm unable to provide a say understanding in terms of 3D. But say we have this surface which is say bulging, right? So at this point also you have the curvatures. At every point you have, we look at that. Of course, we would understand curvature by say inserting some sort of a curve here, embedding some sort of curve in the surface, and then looking at that how much the curve is curving in that sense, how much curvature does the curve have. So here in one way is, of course, here it's not very easy to explain it from using tangent vectors. So what we do is recall some time back, and I'll just make it some of a twisted, not a twisted, just a inverted surface. At every point we had, at every point P vector, we were able to define what we call as a tangent plane, which had a normal vector NP. Right? At any point, at any other point, you have this q vector here. It will also have some sort of a tangent. So it will be TQS, and this was TPS. And it will also have some normal vector N and NQ. Right? So we want to measure. So it's like the change in the normal vector gives us in the local neighborhood, right? In the local neighborhood, the local neighborhood of a point P vector, of a point P vector gives us an, a measure of curvature. Right? So you'll ask, okay, fine, but how? The thing is, if you bring both these normal vectors together and then set it at the same point with a common point, then we see that this was NP and this is NQ. And you can clearly see that they are not aligned. Right? There is some angle between them, or they are not aligned in that sense, which means that there is some there is curvature, which means that this surface has curvature. This surface has some curvature. So so happens that the normal vector, right, the rotation of the normal vector or the tilt of normal vector or the variation of normal vector, that tells us how much the surface is curving. And we'll be using those ideas to understand curvatures, to measure the curvature. And that is what we'll be discussing in the next class. But for today, let's also end it with a particular note. Say for a flat surface, the normal vector is the same everywhere. It points along the same direction for a flat surface. So it means that n vector is always aligned. If you take p vector and q vector, they all fit in the, they are and aligned, they are aligned actually. So that is the reason a plane has no curvature. So either we can clearly say that alignment of normal vectors in the local neighborhood, that gives us a measure of how much curvature the particular surface has in the local neighborhood. So it so happens that a curvature, as we recall from the from our the portion on curves, is that curvature is a local property, right? Curvature is a local or is a point property. It varies from point to point in general. It's only in specific cases like that of a plane where the curvature is zero throughout. But in general, it's a point property and it varies from point to point on the surface. So yeah, with I think with this we would like to I think I would like to close the session today, because then we would discuss about second fundamental form we'll introduce. Before that, we'll have to talk about what are maps, with what are these Gauss maps. So once we understood Gauss map, then we would also bring what is known as Weingarten map, and in simultaneous we'll also be talking about what is the second fundamental form. And once that is set, then we can define all sorts of curvatures, the principal curvatures, Gauss curvature, mean curvature, then even furthermore into geodesic curvature. So that's the plan as of now. Yeah.
Yes, I have a query here. So in the
Sure, sure.
first fundamental theorem, I
Yeah.
mean, which characteristic of the surface are reflected by these values EF and then G?
Yeah, so we see that when we construct E, F, and G, right,
Yes. I mean,
we
which
require,
characteristic of the surface? Yeah.
so here we only look at the local behavior, only the tangent, so to speak. If you see, right, it's just the dot product between the tangents. So it only tells us, and tangent is what is required to compute lengths,
Yes.
right? So which means that first fundamental form by its very form, it only captures lengths.
Yes.
And in
Yes.
second fundamental form, just to give a preview, we have what you call, we have double derivative or second, I mean the second derivatives. And you know that second derivative tells us and gives us an idea about how much a tangent is also changing.
Right. Yes.
Yeah,
Yes.
yeah, and then there is where that's how we introduce that's how we are able to get a measure of curvatures from the second fundamental form.
Yes.
Yeah, so
And would you
that's
be
what.
covering? Yeah. Yeah. Thanks. And would you be covering tensors in the next class, or for the? I mean, in the next class, I mean, which broadly which topics would be covered?
Yeah, so broadly, actually, I would like to finish surfaces, and I'm skipping a lot of things just because this is meant a very short course, and we have lots of things to cover. So I would be once we define second fundamental form, then we can go very fast. These are all just definitions, so we do not have to spend much time on defining what are principles. They are just, once we have the Gauss-Weingarten map, when we construct a matrix, then principal curvatures are the eigenvalues. The Gauss curvature is just the determinant of the matrix of that matrix. Mean curvature is the trace of that matrix. It's just as simple. These are all definitions.
Okay. Yeah.
Yeah, it's just that we have
Thanks.
to construct that matrix first. Once we construct it, the rest are just straightforward. It's just definitions.
Okay. Sure.
Yeah.
Okay. Thank you so
Yeah.
very
So
much. Yeah.
I'll stop recording. Yeah.
Yeah. Bye then.
Yeah.
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 See you
Yeah.
on
Sure.
Friday.
Thanks. Yeah.